Chapter 16, Moments, Forces, and Accelerations. This is going to look a lot like Chapter 12, where you draw a free body diagram with all of your forces that are acting on an object, just like statics. And when these don't balance, they create accelerations. And the new chunk we're going to add over here is moments. And so when moments don't add to zero, they are going to produce angular accelerations. We're going to attach all of these motions to the center of gravity over here on the kinetic diagram, and we can go through some examples where we take moments around various different points in the system. Just as a review, so moment of inertia, what was that, and what's moments? So recall that moments are a cross product. You have a lever arm, R cross F. Force has to be perpendicular to that lever arm, so it's a cross product. And our position vector goes from like the axis of rotation or any point of interest to where your force is applied or to the piece of the object that you're interested in analyzing. So here's the simplest case scenario: is you have a point mass that's all located at some distance, so like a tennis ball on a string or something. So let's say you have a tennis ball and it is going through some kind of circular motion, so you're swinging it around in a circle, and we want to look at the moment of this ball cruising around some point P. And maybe you're changing the velocity of it, so you have some kind of tangential acceleration, which is alpha cross r. Alpha is your radians per second squared, so this is how the magnitude of your velocity is changing. And then you're also changing the direction of that acceleration. So this is your omega cross r is happening here in the radial direction that's pulling towards the center of rotation. Okay, so if we walk through our moment is r cross force, r cross ma. And let's say we're going to take the moment around this point P. So our position vector is going to go from P out to G. And how I have it oriented here, that's going to be just happening in the I direction. So R, 0, 0, everything is happening in the X direction. And then there's these two components for our acceleration. We've got the tangent is alpha cross R, and it's pointed up in the J direction, versus we have this omega cross R, which will be negative I direction actually. And if you go through this, you'll see that the perpendicular part that we're interested in for moments ends up being this alpha cross R piece of it. So we can ignore omega cross R for a little bit and just concentrate on this m times alpha cross R. That's the piece of acceleration that comes out of the cross product. And when you combine those r's together, you get r squared m alpha. So instead of ma, we have mr squared alpha. And this mr squared pops up over and over again, and people decided to just kind of group this term together and call it inertia. And we have our angular acceleration, so radians per second squared instead of something like meters per second squared. So angular acceleration, our position vector from some point to the object, and then mass. Just a quick comparison of force versus moment. So when forces don't add together, it creates mass times acceleration. If you think about what mass is, so this is a scalar quantity, it's not a vector, but it just resists motion. The acceleration is the vector piece of it that gives force its direction, and mass is just, if you have a big mass, it's hard to move, right? Okay, so compare that to our moment equation. So instead of mass, we have moment of inertia. And instead of meters per second squared, we have radians per second squared. So both equations have some kind of an acceleration, and both equations have a resistance to that acceleration. So just like you think of mass for your force equation, you can think of inertia for your rotational motion and your moment. So translational motion, pushing something in a straight line, the x direction or y direction, versus a moment where you're trying to rotate an object, and inertia is resistance to that rotational acceleration. Remember what inertia is. So it's really dependent on that position vector. So R is how your mass is distributed around that axis of rotation. And maybe you've done one of these experiments in physics or watched ice skaters, that kind of a thing. So the point is, if you increase your radius, you stick your arms out, it makes your inertia much larger. So this is why if you're falling, what do you do if you're falling? You stick your arms out to try and stop yourself. So by sticking your arms out, you increase your inertia and you make it harder to tip over, harder to rotate. So you're going to have a more stable structure if you have a larger R, and it's much more dependent on this R than it is on mass. So get used to really paying attention to how that mass is distributed. If you want something to move easily, you want to give yourself a very small R. So really put that mass tight around your rotational axis, versus if you want something that's stable, that's not going to tip over. So civil engineering versus mechanical engineering. So civil engineering, you want to make a large R, a large inertia that's going to be stable and won't tip over. That's rotational motion, is tipping over. Versus mechanical engineering, if you have machines with moving parts and you want to make it energy efficient and easy to move, then you want to create something with small lever arms, small moment of inertia that's very easy to get that angular acceleration out of. Here's an old diagram from static. So if you're in 2D, let's say you're trying to rotate something around the x-axis. So in that case, your R becomes a distance from the x-axis up to each little chunk of mass that's in your system. And you see that cross product again. So y is 90 degrees to x. And so the inertia around the x-axis is going to be y squared dA. And you can walk through some object. You have a pile of snow or something, and there's some kind of an equation to describe that pile of sand, and you can go through and integrate and figure out how hard it is to rotate around that axis. So if you're looking at the y-axis, then instead of r squared, it's your distance is in the x direction instead to each little chunk of mass of that object. So here's just a really quick example problem. So you have some object and you write an equation that describes the shape of that object, and a lot of times they'll put these guys in some sort of generic form, and so you'll have to actually find a little bit of that equation yourself. So there's tables for a lot of generic shapes and even generic equations that you can skip the calculus and just look things up in tables. So that if you can get a good equation that describes how that mass is distributed, the next little chunk of that is going to be chugging through kind of the calculus piece of it. So x squared dA, where your area, and you can draw in the elements for this thing. So the height times the base, kind of just, the element is like a little rectangle, base times height. And the height is y, that's just that equation for your line, and your base is dx. So y dx is your area. And you just chug in this entire equation. So there's your y times x squared dx, and then you integrate 0 to a, whatever limits you're looking for, and you can get inertia around various things. Okay, so this is the inertia around the y-axis, which means it's distance in the x direction. Okay, so hopefully that's bringing back good memories from statics. And couple more things to look at. So we're going to be looking in chapter 16 at two-dimensional motion, which means the rotational axis is actually going to be coming out in the k direction, so out of the board. So instead of going around the x-axis or the y-axis, this is where we're going to do r squared, and it's just a triangle, right? So a squared plus b squared equals c squared. Or if we're looking at the inertia not around the x-axis or the y-axis, but the inertia around the origin, so 0, 0, or the inertia around the z direction, not x, not y, but z, coming out of the board toward you, you can replace r squared with x squared and y squared, and so it turns out that the inertia around the origin is just a combination of iy plus ix. One thing that a lot of the problems will give you is this radius of gyration. So if it's a point particle like the tennis ball, it is just r squared a. If it's some other object, a hoop or a cylinder or a pipe or something, then it's going to have a different inertia depending on how that mass is distributed around the axis. And rather than making everybody go through the calculus, or maybe it's really a complicated shape and you're just going to experimentally measure this quantity, so what they'll give you is this radius of gyration, and that is an equivalent system kind of a deal. So rather than having the mass distributed as it actually is, what it feels like is it feels like all the mass is at this one radius. So, and they have the symbol K. So instead of going through all the calculus, you're just going to plug in that equivalent radius, and it's almost like the center of mass. So when you say, oh, the center of mass, it behaves like all of the mass is located at that one point, and we're solving for reactions and supports and stuff. It really does feel like all the mass is at that one point, even though it's not. So that's what the radius of gyration is for rotational motion. So even though all the mass is not located at that one location, it feels, if you're going to rotate it, it feels like that's where the mass is if you're going to rotate it. So just replace your r squared with k squared, and it's the same thing. And that's what, yeah, so I don't make you do any calculus, but just to remember where this thing is coming from and what you're looking at. Another thing to remember is this parallel axis theorem, and also how inertias add together. So let's say we're not taking the inertia around the center of mass. So that's that little bar over it. That would be how hard it would be to rotate around. So B prime, this is going through the center of mass. But let's say I don't want to rotate it around this axis. Let's say I want to come down here and instead rotate it around this axis instead. Okay? And so what that would be is I would take the distance from the axis of rotation all the way up to each little chunk of mass. So let's start with I around a is y squared dA. And what we can do is we can take this radius and we can break it apart. We can say this distance y over here is a combination of how far it is to the center of mass, and then from the center of mass to each element. So y squared is equal to this y prime plus d squared. So you go through this squared, so we have y prime squared, 2d, and this guy actually goes to 0. That's the definition of a center of mass. So if I have half of my mass above and half below, it balances it out, so you have some plus and some minus. This isn't squared, and so it matters if you're going up or down from it. So this term goes to 0, and what you end up with is your inertia around the center of the thing plus area times the distance from the center to your new axis. Okay? So d is the distance from the center of mass to the new axis you're trying to rotate around. And you'll notice that the farther away you get from that center of mass, the harder it's going to be to rotate. So your inertia increases as you get away from rotating around the center of mass. But this is depending on how something is rotating. Remember this parallel axis theorem, that you can pop around and kind of figure out the inertia around any axis that you want if you know what it is around the centroid, and then you just pop it down to the new axis over there. Here's some tables. Wikipedia has some good tables, or if you just get onto a Google image search and say search for common shapes of, and pay attention to the description. Some of these like a solid sphere versus a spherical shell. Those are two very different objects, so if it's hollow or solid. And look at the axis that it's trying to rotate, so a rod rotating around the end versus going through the center. So pay attention to what those tables are actually telling you. But if you compare the inertias of these objects, so just thinking about it, what object here would be hardest to rotate? What here has the largest moment of inertia? Well, hardest to rotate would be where all of the mass is as far away as possible from that axis of rotation. So mr squared, this is 1 versus 0.5 versus 0.6 versus 0.4. So you can kind of think about how that mass is wrapped around the axis of rotation and how hard it is to rotate. And one of the homework problems goes through rolling various different objects down an incline and seeing which one travels the fastest, which one has the largest acceleration based on how that mass is distributed around the axis. And you can come back to these tables and look up the inertias for various different objects of how that's going to change the motion. Another thing to remember about inertia is it's additive. So just like if you have a bunch of different rocks, you'd add together the masses, mass 1 plus mass 2, mass 3. Same thing with inertias. So if you have an object that's, maybe this one is created from a couple of triangles and a piece of a circle, so you would just add together the inertias of each of these objects. And so if you have some complicated system with a bunch of different things that are all connected together, just start with one piece at a time and figure out what the inertia for that one piece is, and walk through the thing. Use the tables to see what the inertia is for each of those pieces. If something is symmetrical, so like 2 and 3 are both triangles and they're both situated, they're kind of mirror images of one another around that axis of rotation, so those will end up being the same. So you can look up what a triangle is and where that's rotating around. And then in the end, you're just going to add together those pieces. So there's 2 triangles and there's one chunk of the circle. And if you add together x and y, that gets you around the k-axis. So crack open that statics book if it's been a while since you looked at some of these inertia problems, because this is what you'll need to figure out for moments. Okay. What if our object is not rotating? You'll remember for statics, we used moments to find reaction of forces. So like here's a beam and we have some force applied to it and we want to figure out what's the reaction at A and B. And even though this system is not rotating, we still need one more equation to solve for things. And so we can't just get everything we need from Fy. So you'd say, well, where should we take the moment around? Let's take the moment around point A. So if we look at the moment around point A, that really quickly gets us FB, and we can go on our way. So these tricks of where you want to take the moment around, and remember you want to take it around the point where you have the most unknowns, because you kind of get rid of some of the forces in your moment equation because of that position vector. So if r is 0, I don't have to worry about Fa, and Fa does not show up into a moment around A equation. So moments are usually the fastest way to solve for things. There's fewer unknowns in them depending on what you take it around. And for the same reason we used moments in statics, even if something wasn't rotating, we'll do the same thing in dynamics. And then thinking about which point we're going to take the moment around, you can play these games of getting rid of forces. Okay, so here's an example problem. And in this problem, the van is just going to be going down the street. It's not rotating, but we are going to use a moment calculation on it. And we'll think about how that works even though it's not rotating. Okay, so we have 30 feet per second speed, the brakes are applied, and The wheel stopped rotating, so I guess it skids to a stop 20 feet. Find the magnitude of the normal reaction and the friction force at each wheel as the truck skids to a stop. Okay, so skidding to a stop means it's accelerating, so we're going to have forces adding to 0. But if you look at how many unknowns we have in this, so the normal reaction at each wheel, so we have what's happening at wheel A, what's happening at wheel B, and we want the friction force. They don't give us a friction coefficient here, so we're going to have to figure that. So we have 3 unknowns. So that means we're going to have at least 3 equations to figure out those 3 unknowns. This is also involving a little bit more than just force and moment. So what is our acceleration going on here? We can use a little bit of kinematics to figure out acceleration. Okay, so start all these problems out by drawing free body diagram and your kinetic diagram. So we have the weight of the car, normal force, friction that is slowing it down on the front and the rear tires, and all of this is going to add together to the van slowing down. And notice in our kinetic diagram, we're attaching that acceleration to the center of gravity of that truck. Okay, this acceleration right here of the truck, can we figure that out from our starting velocity and it skids to a stop in 20 feet? So remember our constant acceleration equations, which one should we use? There's nothing in here about time. We don't need time, so let's ignore these guys and go straight to, we have an ending velocity of 0, we have our starting velocity of 30 feet per second, we know it skids to a stop in 20 feet, so this third equation will be the easiest one to use. And we can go ahead and solve for our acceleration, and this is the same acceleration that will come out of our force balance too. So when we look at what's happening in the x direction, which happens to be the friction forces, those 2 friction forces will add together to what we got from these constant acceleration equations. So there's one piece of the puzzle, and we had to kind of reach back into good old chapter 11 stuff to get that piece of it. Okay, so now that we know our acceleration, we've got our normal forces we have to solve for, friction, so let's start going through the force balance on this thing. So what's happening in the x direction? Friction goes to acceleration. So there's our x direction, and we know that friction is going to be a function of our normal force, so there's no acceleration happening in the y direction, so that means our weight is equal to A and B added together, so we can at least solve for our friction coefficient. We don't know the individual normal forces, but with what's happening in the x direction, now we have our friction coefficient. So woohoo! And we use this acceleration in there to get that. Okay, so there's the x direction. How about the y direction? Can we get any relevant information out of here? So in the y direction, there is no acceleration in the y direction, so these forces add to 0. So we have the normal forces going up, the weight coming down, but I have 2 unknowns here, and I'm not going to really be able to solve for too much in the y direction. So we're going to have to go back to moments. Okay, so if this was that beam problem or something, what would you take the moment around? And the answer is either tire A or tire B. So if I take the moment around one of these 2 points, I don't have to worry about the normal force or the friction force acting through that point. So you get rid of some of your unknowns out of that problem. So let's go ahead and take our moment around point A for this one, in which case we're going from A to where the weight is. So that would be our 5 feet. So we're going forward and the weight is coming down. And if you remember something in the clockwise direction, clockwise is negative, counterclockwise is positive. And get your right hand out and remember how to do the signs on this thing. Okay, so that's A to weight, and then 5 plus 7, so if we're going out 12 feet, That's the normal force at B that we're getting that. And whatever we do on one side of the equation, so this is like how you would calculate a moment in statics, we're going to do that for our kinetic diagram too. So we're actually going to be, let's see, our center of gravity is 4 feet up. So if we go up to the center of gravity, and then we have MA in the x direction, so our moments adding together like statics, but they don't add to zero. They add to the r cross MA, where A is, that's the acceleration of the center of gravity of the van. So whatever you do on one side of the equal sign, do on the other side too. So really think about this new piece of it. So we're going up and then to the MA, and that is, it doesn't add to zero. And that comes from, if we had taken the moment around the center of gravity instead, then it would add to zero. But since we're not taking the moment around the center of gravity, we're taking it around this back tire, it does not add to zero. It adds to the r cross MA. Okay, but the entire truck is not rotating, so we don't have to worry about inertia on this problem. So there's no I alpha, but there is an RMA. Okay, so you chunk through this, and the only unknown in this is going to be that normal force at B. So now we have normal force at B. We can go back to everything in the y direction and get A and solve for everything. So in this case, the truck is not rotating. We don't have to worry about inertia. If we took the moment around the center of gravity, that would be zero. But taking it around this different point, taking it around point A, this back tire, it's not adding to zero. It's adding to this r cross MA. So kind of keep track of what point you're taking things around, and think about what that's going to add together to. Okay, this video is getting kind of long, so I'm going to save the next example for the next go around.